Imagine a massive metropolitan hospital just goes completely dark. And I am not talking about the electricity.
Right, because, the backup generators always kick in for that kind of thing.
Exactly. I mean, the data goes dark. Suddenly, like all the patient records, the real-time surgical schedules, the medication allergy histories, they are just, well, they're gone. Unreachable.
Wow. Yeah, that is a terrifying scenario. I mean, in that moment, the difference between life and death literally comes down to the invisible digital plumbing running beneath the hospital's floors,
Yeah, and we normally never think about that plumbing. We picture a digital file as just, I don't know, a little weightless icon on a screen. You double-click it, it opens.
Right, but look under the hood of a hospital or like a global bank, and that file is part of this raging, unstoppable river of information.
To keep it flowing, that plumbing has to be basically a titanium fortress strapped to a rocket engine.
Which is pretty much the absolute definition of mission-critical enterprise architecture. I mean, there is zero room for error.
None. So today, we are taking a deep dive into the literal blueprint of that architecture. We've got a highly focused study guide for a really grueling certification. It's the NS0-165 exam.
Oh, man, yeah. For those not deep in the IT weeds, that is the NetApp Certified Data Administrator exam for ONTAP.
Right, ONTAP being, one of the most widely used enterprise data management operating systems on the planet.
And we should definitely set the stakes right away for you listening. We aren't doing this to just read off flashcards so someone can pad their resume.
Oh, absolutely not.
This material is a literal masterclass in how massive organizations actually build systems to keep their most critical data secure, incredibly fast, and online 24/7.
Yeah, by looking at how they test the engineers, we really get to see the underlying physics of the internet. So to give you a sense of what these IT professionals are actually up against, let's look at the hard facts of this exam.
It's intense.
It really is. It is a 90-minute test. You are hit with 60 questions. It's delivered in English and Japanese, and the passing score is exactly 64%.
Which, is a number that tricks a lot of people. I mean, in a high school math class, a 64 is basically failing.
Yeah, it sounds incredibly forgiving.
It really does.
Okay, let's unpack this, because while 64% might sound like a low bar, the sheer breadth of the concepts covered in these practice questions is just staggering.
Oh, for sure. The test formats aren't just simple multiple choice.
Right. They throw multiple selection, matching, and these complex drag-and-drop scenarios at you to simulate the actual pressure of sitting at a command console.
Because you aren't just tested on one narrow networking skill. You have to understand, deep cryptographic security, complex routing protocols, and automated disaster recovery.
All at the same time.
Exactly. The depth required to even guess intelligently on these questions is immense.
Because the margin of error in a live enterprise environment is zero. If you guess wrong in the real world, the hospital goes offline.
Yeah, so the test throws every possible failure scenario at you to see if you actually understand the underlying mechanisms, not just, the textbook definitions.
So we're going to explore 10 specific practical questions from our source material that perfectly illustrate this. Let's start with the ultimate baseline. Before data can be fast, it absolutely must be secure.
Security is always step one.
Right. So the first section of our guide dives immediately into protecting data from external ransomware, internal mistakes, and, honestly, even the system administrators themselves.
That last point is usually the hardest for people to grasp.
Oh, totally.
In enterprise security, the person with the keys to the kingdom, like the senior administrator, is often your biggest vulnerability.
Right. Whether through a compromised password or, well, malicious intent, admin access is the ultimate threat vector.
Which brings up a really fascinating scenario from question 1 in the study guide.
Yeah, so the exam asks how a storage administrator can ensure that specific, highly sensitive data cannot be modified or deleted, even by an administrator, for a set period of time.
And it throws a few curveballs at you as options, right?
It does. It suggests using basic file system permissions, or creating read-only snapshot copies, or just putting the data on an encrypted volume.
But if you analyze those incorrect options, you see the traps pretty quickly.
Right, like basic permissions. An admin can just change them back.
Exactly. Read-only snapshots. An admin has the authority to just delete the snapshot.
And encryption.
Well, encryption just scrambles the data so someone without the key can't read it, but it certainly doesn't stop a rogue admin from simply wiping the entire drive.
Exactly. So the correct answer the exam demands is a feature called SnapLock Compliance Mode. The guide explains that this is designed to enforce strict data immutability for regulatory and legal requirements.
Immutability is the key word there.
Right. Once that data is written to a SnapLock compliance volume, it cannot be modified or deleted by anyone until the retention period expires.
And we mean anyone, not the chief technical officer, not the engineer who physically built the server rack. If a financial institution sets a retention policy for 7 years to comply with SEC regulations, that data is locked in stone. The system actively alters the storage geometry to reject any modification commands.
I love thinking about this like a time-locked bank vault. You spin the dial, set the timer for 7 years, and shut the heavy steel door. At that point, even the bank manager doesn't have the combination. It literally does not matter who shows up with a warrant or a demand to open it.
Right. The physical mechanics of the lock simply will not allow it until the clock runs out.
That level of absolute certainty is exactly what legal regulators demand. It removes human error, coercion, or malice from the equation entirely. The machine just takes over the enforcement.
But security isn't just about locking files from deletion, you know. It's also about encryption, which brings us to question 2.
Ah, yes. Question 2 deals with how to manage the actual encryption keys. The scenario asks, when you are configuring the onboard key manager for encryption, where is the master key material stored?
And the correct answer is?
The correct answer is that the master key material is maintained within the internal cluster database. Now wait, storing the encryption master key inside the very cluster database it's supposed to be protecting. Isn't that like locking your front door but leaving the key permanently glued under the doormat?
I totally get that reaction. What's fascinating here is that it sounds like a terrible idea at first glance.
It really does.
But it's actually a brilliant piece of engineering that solves a massive real-world problem. To understand why the exam wants you to choose the internal cluster database, you have to look at the nightmare of managing external key servers.
Okay, lay it on me.
Historically, enterprises bought separate, highly secured physical appliances just to hold encryption keys.
So you have your massive storage servers in one rack and a smaller safe holding the keys in another rack.
Precisely. Now imagine the network cable connecting those two racks gets unplugged, or like the switch between them restarts.
Oh no.
Yeah. Suddenly, your storage system can't talk to the key server. In an instant, your entire data center loses access to its own data. It locks itself down.
Just because it's a cable.
Right. By relying on an external device, you've introduced a single catastrophic point of failure just to hold a key.
Ah, I see. So by using the onboard key manager, or OKM, you eliminate that external dependency. But how is the doormat secure in this case?
Because the internal cluster database in ONTAP isn't just a simple file, it is a highly secure, heavily encrypted, and intrinsically protected distributed ledger that lives across multiple physical nodes in the system.
Okay, that makes more sense.
It balances the rigorous security of enterprise encryption with the operational reality that your keys need to be securely available right where the data is being processed, without relying on fragile external connections.
That makes perfect sense. Maximum security, but practical deployment. However, a perfectly secure vault is absolutely useless if it takes an emergency room doctor 10 seconds to pull up a patient's chart.
10 seconds is a lifetime in IT.
It really is. Yeah. Which moves us to a massive chunk of this exam performance. How do enterprises move massive amounts of data without creating bottlenecks?
Well, in a modern enterprise, slow data is essentially offline data. If thousands of applications are all competing for the same storage resources at the exact same millisecond, the system has to have a way to prioritize.
Let's look at how the exam handles that traffic jam. Question 3 asks about the primary benefit of using quality of service, or QoS, floors on a shared storage system.
And the guide tells us the answer is guaranteeing a minimum performance level.
This directly addresses what IT engineers call the noisy neighbor phenomenon.
Exactly. Yeah. Imagine a shared storage environment where you have critical financial databases running right alongside a massive routine data backup.
Okay.
If that backup suddenly tries to hog all the processing power, your critical database gets starved.
Here's where it gets really interesting, because I like to picture a shared storage system like a massive, congested city highway. You have daily commuter traffic standard emails, internal memos, all trying to share the road with ambulances.
That's a great analogy.
A QoS floor is basically an HOV or VIP lane that gets painted directly onto the highway for your ambulances. It ensures those critical workloads always cruise at top speed.
Yep.
It guarantees a minimum flow, usually measured in input-output operations per second, or IOPS, regardless of how backed up the rest of the traffic is.
That's a perfect way to visualize it. Setting a QoS maximum limit stops a workload from going too fast, but the QoS floor is what ensures your most important application never drops below its required baseline.
Right.
The exam tests this because guaranteeing performance is just as critical as providing raw storage capacity.
So we have our VIP lanes. But what happens when the sheer volume of traffic is just too big for one city to handle? Question other. 6 tackles massive scale.
Scale is huge on this exam.
Yeah, so the scenario is that an administrator needs to scale a single namespace across all nodes in a cluster to handle a massive file count. The required technology, according to the answer key, is a flex group volume.
Right.
What is a single namespace and why is the file count such a big deal?
If we connect this to the bigger picture, you have to realize that historically, a volume of data was tied to a single physical storage controller like one brain in the cluster.
Okay.
But modern enterprises generate insane amounts of data. Think about a major animation studio rendering a feature film. They are generating billions of tiny image files.
Billions. Wow.
Even if a single storage node has the hard drive space for it, its processor simply cannot manage the metadata for billions of files. It hits an artificial ceiling.
So how does a flex group break that ceiling?
Well, a single namespace simply means that to the end user, or the rendering application, it still looks like one giant continuous folder.
It hides the complexity.
Exactly. But behind the scenes, a flex group automatically distributes that single folder across multiple constituent volumes living on every single node in the cluster.
That's really smart.
It takes the processing burden of managing those billions of files and spreads it evenly across all the available brains in the system.
So it's a massive delegation strategy. Which logically brings us to question 7, which tests how the data actually travels from the storage nodes to the user.
Ah, the protocols.
Yep. It asks about the most significant performance improvement in the NFS version 4.1 protocol compared to the older version 3. And the correct answer is support for parallel access to data across multiple nodes.
Before we compare them, let's establish that NFS, or Network File System, is a standard protocol. It's basically a language computers use to ask for files over a network.
Okay, got it.
With the older NFS version 3, even if you had this massive flex group spread out across 10 nodes, a client computer often had to talk to one single specific node to get its data.
Oh, like going to a giant supermarket that has 50 registers, but you're only allowed to use checkout lane number 3.
Exactly that. It creates an instant bottleneck at that one door.
Right.
But NFS version 4.1 introduces parallel access, specifically a feature called PNFS. Now, the client computer is given a map of where all the pieces of the file live across the cluster.
Oh, wow.
Yeah, so the client can talk to all the checkout lanes simultaneously, pulling different pieces of the data from different nodes all at once. The speed increase is astronomical.
Parallel access. That is brilliant. And the exam doesn't stop pushing for speed there. Question 8 hits on another upgrade, this time at the hardware network layer.
NVMe.
You guessed it. It asks for the advantage of a protocol called NVMe over TCP compared to traditional ISCSI. Now, I know ISCSI is a very common, older way to connect storage over an Ethernet network.
No, very common. It's everywhere.
Right. And the correct answer states that NVMe over TCP provides lower latency and reduced CPU overhead. But I have to ask, if ISCSI works fine, why are enterprises ripping it out to replace it with NVMe over TCP?
Because at modern enterprise speeds, working fine is actually a liability.
Really?
Yeah, this is entirely about compute efficiency. ISCSI requires a lot of translation. It takes native storage commands, wraps them up in heavy network packets, sends them across the wire, and then the receiving end has to unwrap and translate them back.
This sounds like a lot of work.
It is. That translation requires CPU power. At 10 gigabits a second, it's manageable. At 100 or 400 gigabits a second, your CPU is spending all its time just translating languages instead of actually processing data.
Oh, wow. So the CPU becomes the bottleneck, not the network.
Yes, exactly. NVMe over TCP strips out that heavy translation layer. It allows lightning-fast solid-state drives to speak their native language directly over standard Ethernet networks.
It just cuts out the middleman.
It drastically lowers the friction. You get the crazy low latency of modern flash storage without having to buy exotic, specialized networking cables. You use the standard TCP IP network you already own, but you optimize every single micro bottleneck.
Okay, so we've built a system that is an ironclad vault, and we've turned it into a race car that leverages parallel processing and native hardware languages to fly down the track.
Which is great until
the terrifying reality hits hardware fails. Drives die, backhoes cut fiber optic cables, power supplies literally catch on fire. The final set of practice questions focuses entirely on the safety net.
Because a system that fast and that secure is totally useless if a single burned-out cable takes it offline. The exam demands that administrators know how to orchestrate automated survival.
Question 5 addresses exactly this local survival. It asks, in ONTAP networking, what is the purpose of a failover group? The correct answer is to define the set of network ports available for a logical interface. Can we translate that into plain English?
Certainly. A logical interface, or LIF, is essentially the IP address that the hospital applications are talking to.
Okay.
That IP address lives on a physical Ethernet port on the back of the storage server. If that physical port suddenly dies, maybe a switch fails or a cable is pulled, the system needs a predefined backup plan. It can't wait for a human to run into the server room.
So the failover group is a pre-approved list of backup ports. It's like a perfectly choreographed relay race. If a runner trips and falls, another runner from the failover group instantly teleports into their place, grabs the baton in midair, and keeps running.
And it happens so fast that the application accessing the data just experiences a tiny microsecond pause. The connection is reestablished on a healthy port automatically, and the data keeps flowing.
So the doctors pulling the patient chart don't even realize a piece of hardware just died.
They have no idea.
But local hardware dying is one thing. What if the disaster is bigger than a single port? What if an entire data center loses power due to a massive storm?
That's where it gets really complicated.
Yeah, and that brings us to question 9. It asks, when configuring a metro cluster over IP, what is the critical hardware requirement for the back-end interconnect? The answer is dedicated high-bandwidth IP switches.
To understand why this is a massive exam topic, we have to understand what a metro cluster is. It is an active disaster recovery solution.
Okay.
It is designed so that when you save a piece of data to Site A in New York, the system does not acknowledge that the save is complete until it is simultaneously written to Site B, which might be 50 miles away in New Jersey.
That's synchronous replication. The data literally has to exist in 2 physical locations at the exact same moment before the system considers it safe.
Yes. And this raises an important question about the unforgiving physics of the speed of light and network latency.
Wait, really?
Yeah. If you try to send that synchronous traffic over a shared corporate network, or worse, a public internet connection, you introduce unpredictable delays. Someone downloading a massive file somewhere else on the network could delay your write acknowledgement by 50 milliseconds.
And I'm guessing 50 milliseconds is bad.
In the enterprise storage world, 50 milliseconds is an absolute eternity. Because the primary application in New York is paused, waiting for New Jersey to confirm the save, a 50-millisecond delay on the network drags the performance of your primary billion-dollar database to a grinding halt.
Oh, wow.
You need dedicated, massive bandwidth switches so that the pipe between the 2 sites is always clear, always predictable, and incredibly fast. The data consistency must never be compromised by network weather.
That zero downtime mandate carries right into question 10, which asks what action is necessary to upgrade a cluster while maintaining continuous data availability. The answer is using a rolling or batch upgrade process. There's no maintenance window on a weekend where the whole system goes offline for an hour.
Zero downtime is no longer a luxury, It is the baseline expectation for any enterprise.
Yeah, a global logistics network cannot pause container ships because IT needs to update software.
Exactly. A rolling upgrade means the system moves the workloads off Node 1, upgrades Node 1, brings it back online, and then repeats the process for Node 2. The engine is literally being rebuilt while the car's driving down the highway at full speed.
And to orchestrate all of this, the immutable security, the parallel performance tuning, the automated failovers, and rolling upgrades, you need a serious command center.
Which brings us to the last piece.
Yep. Our final question, question 4. It asks which tool provides a unified view for monitoring system health, performance, and capacity risks across multiple clusters. The answer is ActiveIQ Unified Manager.
When you have dozens of clusters, hundreds of nodes, and petabytes of data spread across the globe, you simply cannot log into each system individually to check its health.
That would be impossible.
Right. ActiveIQ Unified Manager is the centralized dashboard. But it's not just a passive monitor. It uses predictive analytics to spot trends. It warns the administrators about capacity risks or performance bottlenecks weeks before they become actual outages.
Thank you for joining us on this deep dive into the invisible digital infrastructure that holds our world together. Keep questioning how the tech around you actually works, and we will catch you next time.